Hi, I'm Joan Marie. Thanks for tuning into my talk, where I'll tell you about all the work I've been doing in central Appalachia to understand how hillslope processes change with climate. There's an ongoing debate as to whether the onset of Quaternary cooling increased terrestrial erosion globally. Some studies of thermochron and offshore sediment accumulation point to higher erosion and accumulation in the past 2 million years, while other studies show either no change in erosion or highlight the temporal biases inherent to measuring erosion rates in Earth's history. In particular, thermochron isn't helpful in landscapes with slow enough exhumation rates that wouldn't have responded to Quaternary climate change. Sediment flux from uplands also goes through a sometimes convoluted storage and transport journey to the ocean, introducing complexities that mask any climate-modulated signal. Not to mention that none of these techniques clarifies how erosion processes might change with climate. So to better answer these questions, one of the goals of my research is to target more direct records of erosion in the form of hillslope colluvial records. In terms of cold climate erosion processes, whether or not you can determine if glaciers erode more quickly than, say, fluvial incision, at least the process change is evident in landscape form and stratigraphy, so measuring the erosive power of glaciers versus rivers is a little more straightforward than understanding the contrasts in cold but unglaciated landscapes. We know a lot less about periglacial landscapes, which are driven by permafrost processes, occurring today in high latitudes but covered mid-latitudes at times of glacial maxima. So with this study, I'm going to try to determine whether mid-latitude unglaciated regions experience heightened erosion rates in cold climates compared to temperate conditions. The few studies and numerical models that have tackled this problem imply that cold climates are more erosive than warm ones. On the Oregon Coast Range, cosmogenically derived erosion rates from Paleolake sediments were highest during the cold periods of the core. Likewise, in the Potomac River Basin, meteoric beryllium-10 was highest in sediments deposited during cold periods, which the authors attribute to heightened stripping of topsoil by periglacial erosion compared to warmer periods. My study is just north of the Potomac River in central Pennsylvania, which sat about 100 kilometers south of the last glacial maximum and was underlain by permafrost during this cold period, and there's plenty of topographic evidence for the existence of permafrost and periglacial processes. LiDAR mapping reveals features like solifluction lobes and mass movements that are characteristic of modern permafrost environments. The preservation of these features long after permafrost disappeared implies that sediment flux during cold periods was much higher than the modern warm climate. The fact that 10–15,000 years of warmer and wetter climate and bioturbation has done very little to erase these cold climate features, which prompted us to try to quantify the landscape's erosion response to these changes in climate. To answer this question, we work in headwater valleys in the Valley and Ridge physiographic province, where folded sedimentary units act as great structural traps for colluvial records of erosion. Our work at Garner Run in 2018 gave us a preliminary answer, and I'll present new data from our second site, Bear Meadows. At both of these sites and elsewhere in the Valley and Ridge, ridgelines are composed of fractured bedrock debris and erode slowly, about 10 meters per million years. Downslope, meters-thick blocky debris drapes steep hill slopes and broad toe slopes, often taking the form of these solifluction lobes. These boulders armor hill slopes and channels, apparently contributing to the preservation of these valley bottom geomorphic features. So in order to quantify the geomorphic impact of these climate-modulated processes, we used cosmogenics to measure the residence time of regolith and valley fill. We asked, were these features created at the last glacial maximum, or have they been around for much longer? Cosmogenic nuclides accumulate at Earth's surface such that we can use them to say how long material has been exposed at the surface, or how quickly a surface is eroding. The more beryllium-10 a sample contains, the slower the erosion rate, or longer time that material has been exposed. We can also measure two nuclides, whose production occur at a constant known ratio, but whose half-lives are different, leading to different decay rates. This technique allows us to back-calculate how long buried material has been shielded from surface radiation to give us a burial age of sediment packages. For example, sediments exposed at the surface contain concentrations of aluminum-26 to beryllium-10 at a ratio of about 6.5 to 1, but once that material spends time buried, aluminum decays faster, and that nuclide ratio goes down as burial time increases. We use these principles to track residence time of material at our watershed. When we measured the beryllium-10 in surface samples, we found that regolith had a long residence time, between 50 and 100,000 years, and we used stream sediments to measure a catchment erosion rate of about 7 meters per million years. When we measured the aluminum to beryllium ratio in material from a valley bottom core, we found that the upper 4 meters was buried recently, but material below that was buried much longer ago, maybe 350,000 years ago. These results clearly demonstrated that this landscape was a product of more than just the most recent cold period. A key implication from our burial dates in particular was that it allowed us to compare short timescale accumulation of periglacial debris to long-term erosion rates. Using geophysical imaging, we quantified the volume of debris stored in the valley and converted that volume into bedrock erosion from hillslopes. If we take the long-term erosion rate as that 7 meters per million years we found from the stream sediments, we find that it would take about 300,000 years of bedrock erosion to accumulate the valley fill, which is about the same timescale of accumulation of our core material, which we independently dated. This implies that at our site, the pulsed erosion and accumulation of periglacial debris, which might only occur at transitions from cold to warm climates, is equivalent to the long-term erosion when integrated over an entire glacial-interglacial climate cycle. Or, to put it simply, periglacial processes set the erosion rate in this landscape. To determine whether this idea holds in other landscapes, we targeted a second sandstone watershed, this time at Bare Meadows, which boasts a modern peat bog which has a finer resolution record of late Pleistocene landscape change, which is the focus of some of my other work, but today I'll tell you about the new Hillslope core at this site, which we actually drilled through one of those solifluction lobes in the hope of examining these pulsed accumulation events in higher detail. We ended up collecting 18 meters of core, which seemed to be composed of two different units. The upper 6 meters looked like the periglacial debris at Gardner Run, quartzite clasts with a reddish clay matrix. This package sat atop a browner, sandier unit that appeared to lithify towards the bottom of the core. The ratio of titanium to zirconium in these sediments, which we're taking as a fingerprint for the parent material, indeed implies that these units derive from two different sources. And the concentrations of cosmogenic nuclides in the matrix material also implies these units have two different histories. The top 6 meters has relatively high concentrations of beryllium-10 and aluminum-beryllium ratios that look a lot like we saw at Gardner Run, modern at the top and older below it. But the rest of the core was pretty weird. It contained an order of magnitude less beryllium-10 and had higher nuclide ratios, which, if you remember, wouldn't make any sense if the older deposit was buried before the rest of the core. I hypothesized that this might instead be the signature of a soil profile that was steadily eroding in place prior to being buried by periglacial debris. I had to tweak the forward model I used at Gardner Run to account for this new setup, which goes like this. First, I solve for the steady-state concentration of a soil profile eroding steadily at a given erosion rate. Then, I simulate colluvial packages eroding into and depositing on top of whatever was under it before. I performed this forward model to reconstruct both the timing of deposition events and the erosion rate associated with the paleosurface under the periglacial debris. Now, because we're dealing with deep samples and material that has potentially long residence times, we need our nuclide production models to account for all production, including from muon reactions. While most applications just need to account for spallation reactions via high-energy neutrons at the Earth's surface, muon particles penetrate more deeply into the rock and can produce nuclides at a relatively slower rate but at a greater depths, making them crucial for interpreting any results from below a few meters deposit or a slowly eroding setting. At my site, we have both, so in order to do the best possible job, we used Greg Balco's muon production script that models the downward propagation of the surface muon energy spectrum, which he refers to in his 2017 paper as Method 1A. This model, along with the various exponential function approximations used in other studies, all have subtle but important differences in how aluminum and beryllium are produced, such that the ratio-based interpretations are going to be sensitive to the model we choose. Like I said, we tried to use the quote-unquote best model we could, but any tweaks to our understanding of muon production is going to change our answer. So on the left is the forward model scenario that best fits our data, where the dashed lines are the standard deviation of our Monte Carlo simulations, which account for uncertainty in production rates. In reverse chronological order, we have recent deposition of the first 3 meters, which covered a deposit that was older than what we saw at Gardner Run, about 600,000 years ago. Interestingly, both the newest and the oldest deposit have very similar starting nuclide concentrations, implying that they were subjected to similar hillslope histories prior to their burial. That deposit covered a soil profile that was eroding at roughly 5 meters per million years, which, if you recall, is not that much different than our modern rate of 7 meters per million years we found at Garner Run. I'm interpreting the series of events to look like this. In the late Cenozoic, regolith profile was thick and deeply weathered until periglacial processes turned on, when it got cold enough to support permafrost at the Pleistocene. Thawing permafrost destabilized slopes and produced the erosion surfaces and colluvial deposits we see in the core, the most recent of which occurred in the LGM. And the fact that we don't see a huge change in the erosion rate with the onset of periglaciation tells us that the shift to periglacial erosion mechanisms didn't change the long-term erosion rates at our site, just when the majority of the erosion happens, which again, I'm hypothesizing to be the cold-warm transitions associated with thawing permafrost. I'd like to think my observations go hand in hand with the meteoric beryllium interpretations from Portenga et al. That I mentioned earlier in the talk. Periglaciation doesn't necessarily accelerate bedrock erosion, it just promotes the stripping of soils from hillslopes. So two of the main implications for this work is that first, it's a confirmation that permafrost and periglacial processes have played a role in shaping the central Appalachian landscape long before the LGM. Here I'm showing you data from Alden's work at Hickory Run Boulder Field, a boulder field to the northeast of my site that also has a strong pre-LGM signature of boulder exposure ages, which they attribute to periglacial erosion as well, along with exposure time of ridgeline outcrops. If I overlay the timing of deposition of periglacial debris at my two sites over the oxygen 18 isotope curve, you can see the number of potential glacial terminations associated with periglacial activity, including and especially the Illinoisan, which is more consistent with the Garner Run deposition event if we recalculate deposition with my improved forward model. Of course, one problem here is that uncertainty associated with measuring and modeling cosmogenic nuclides means that deposit dates have error bars that are usually too big to pin down for a specific time frame. You don't want to draw too strong of conclusions when your interpretations are plus or minus 80,000 years and glacial terminations happen every 100,000 years. But improved measurements and concurrent studies of maybe speleothems in Appalachian caves might elucidate when conditions for permafrost were ripe in the Pleistocene. I also suspect that this landscape experienced periglacial erosion each glacial termination, but evidence doesn't always get preserved because the newest periglaciation can erode through earlier deposits, explaining why we don't see, say, the Illinoisan at Bare Meadows. The second implication goes back to the beginning of my talk. Can we say anything about erosion rates responding to permafrost processes on the short and long term? Consider the data. The modern erosion rate at nearby Garner Run is on the high end of our range of possible paleoerosion rates at Bare Meadows, and both of these rates are at the low end of the regional trend of erosion rates in sandstone catchments in the valley and ridge. We'd probably have to perform this study at a number of valley and ridge sites to determine whether there is truly overlap in erosion rates pre and post periglaciation. Contrast that with the regional data that shows that the Susquehanna River Basin is eroding more quickly than both our sites and more quickly than the Potomac River Basin as a whole, the latter of which Portenga et al. Attribute to the fact that the Susquehanna River Basin is closer to the LGM ice margin and therefore had more vigorous periglacial erosion. It would be great to keep collecting data for these uncertainties to get reined in, but there will always be the challenge of slow erosion rates and muon production uncertainty, which makes discerning any change in erosion really difficult. But this study is really one of the first of its kind to leverage deep cored material to infer how changes in erosion process affected erosion rates, so at least it's a start. So I'm going to leave you with these two big conclusions from my work. The first of which, in our landscape in central Appalachia and probably in a lot of other mid-latitude settings where uplift rates really aren't that high, the last glacial maximum and previous cold periods resulted in widespread reorganization of regolith on hillslopes via periglacial processes on the order of 3 to 4 meters worth of erosion and deposition. And the second is that cosmogenic nuclides in our topographic analyses imply that first, periglacial erosion sets the modern long-term erosion rate for these landscapes, integrating over glacial interglacial cycles, and that according to our new analyses here, periglacial onset did not necessarily accelerate bedrock erosion compared to the previous climate under late Cenozoic conditions. But I think we still have a lot to learn about how these muons work and how these landscapes work, so stay tuned if we learn anything more. Thanks.